Hi there, I'm Professor Patrick Degener and this is Bioelectronics. In this lecture I want to cover the process of how charge moves from the inside to the outside of the cell and vice versa, and this is the basis for cellular bioelectronics. And in particular I want to then cover towards the end the Nernst equation and the Goldman relation. So, first of all, let's think about what cells are. So, here's a fluorescent image of a cell, which is somewhat complex. So, what we like to do in this course is to simplify things, and we can simplify things by drawing this kind of nice circular, should be spherical, but in a 2D space, this is circular structure. And the actual wall of this structure is the cell membrane, this structure here. The cell membrane, again, is quite complex. There's all sorts of proteins and different things on the surface, but we're not really interested in the molecular mechanics and how, some of the viruses get in and out of the cell and so forth. We're really interested in how ions get inside of the cell and outside of the cell, and the basis for bioelectronic charge movements. So the most important components of these cell membranes are channel proteins and then something else called channel pumps, which I'll describe in the next couple of slides. So we can we can sort of draw these structures in very simple terms as ion leakage, pumps, and channels, to really simplify things so that we can understand this from a more global perspective. So the first thing in terms of ion movement through these cell membranes are what are called passive transport. So the first is membrane leakage. The membrane's not a wall, it's a semi-permeable membrane. It's not perfect, it's not solid, it's semi-liquid. The second are that cells naturally have these aquaporins, which allow traversal of water in and out of the cell. And this is actually quite important because if too much pressure built up, the cell membrane could rupture. As I said before, the cell membrane, it's not a solid wall, it's a very weak structure. And then the final aspect are what are called channels. Now these channels, they act as gates, like mini transistors, if you like, but they also leak, and the leakage across that channel is one of the key mechanisms for charge transport. Now again, when we think about channels and passive structures, the charge is moving just due to differences in concentrations. So this is diffusion. There's no additional energy put in to move charges in one direction or the other. So if we look at channels in particular, we can think of these as voltage gated channels, or these are the most important ones. And if you put a voltage across these voltage gated channels, and actually it's less of a voltage, it's kind of a negative process, well then what happens is that the channels open up, and this allows movement of charges in and out of a cell respectively. Now the movement of charge again is with the concentration gradients, so it can move from a high concentration to a low concentration, not vice versa. So again, there's no energy expended in this process. A few other channels to note: mechanical receptors. These are things on your fingertips that sense pressure, and again, once the pressure goes in, ions can flow in and out of a cell, and this is one of our sensing mechanisms. There are related things to do with temperature, but the most important in terms of the basic cellular electronics are the chemical receptors, which will be very important later on, especially for neurons when we think of neurotransmitters, glutamate, serotonin, acetylcholine, GABA, and so forth. So the final form of transport across the membrane are what are called pumps. So pumps allow traversal against the gradient. And what pumps tend to do, they pump sodium out of the cell and they pump potassium into the cell. Now, because this is against a gradient, this requires additional energy in the same way that it requires energy to, to lift you up a mountain, to go against gravity or against the gradient. This energy comes in the form of adenine triphosphate, or ATP. The ATP is converted to ADP, adenine diphosphate, and that loss of a phosphate gives the power to that system. So it's a bit like the petrol in a car, if you like. Now, what's interesting to us as bioelectronic engineers is not the the cellular, or the molecular sort of methodologies, but we're really interested in turning this into some kind of circuit that we can easily understand. And as per before, we can create this structure, the circular structure, which we will call the cell, even though cells are not necessarily circular. And this will have a number of components. So the first component will be pumps, and this will, as we described before, pump sodium out, pump potassium in. It will have channels, which when opened up, allow, depending on a particular channel type, will allow a particular ion back into the cell. There is passive leakage through these individual channels, and of course just through the channel membrane itself. And we can separate that out per ion, or we can just have an overall leak if we have got multiple components. And then of course this, because there's now charge on the inside and charge on the outside of this membrane type wall, we can think of the capacitance of the cell membrane. So this relates to the area of the whole cell, and of course the distance the thickness of that membrane. And then finally, as there's now going to be different quantities of charge or different concentrations of charge on the inside compared to the outside, charge over capacitance will create a voltage, and we call this the membrane voltage. And this is the voltage on the inside of the cell, the intracellular space, compared to the outside, or the extracellular fluid. And we can treat that extracellular fluid in essence like a ground, as something that doesn't really change very much. So this is our basic electrical model of the cell, specifically the neuron cell, but it's not just neurons, muscle cells, cardiac myocytes. There are lots of cells which operate in a bioelectronic fashion. So let's think about how we take this and turn it into some more standard electronic model. So as we said before, we have pumps, with the pumps are continuously pumping sodium out, pumping potassium into the cell. We have this intracellular space, but let's think about it in terms of a particular ion. This ion may be sodium, potassium, chlorine, whatever, and depending on the type of ion, this will either be a positive or a negative. Okay, and of course then we've got these ion channels which can open up, and the leakage. Now if we think about that as a circuit model, well then we can say, okay, we've got a capacitance, and across that capacitance eventually we're going to have a voltage, which we can think of as the voltage between the intracellular space and the extracellular space. Now, one thing to note, very important, if you compare my notes to other people on the internet, some people will have extracellular at the top and intracellular at the bottom, and sometimes vice versa. Personally, I like intracellular at the top, the inside at the top, outside at the bottom, but because ground is normally at the bottom. So that's my particular preference. In this structure, we have pumps, which merrily pump the ions away. And then we have a mixture of drift and diffusion. We think of this, at least initially, in equilibrium. So what happens, depending on the pumps, there's a charge that there's a difference in concentration between the outside and the inside. There is some leakage. For example, if it's sodium, the sodiums leak back in. This is a diffusion process, but there's also a drift process in the opposite direction. But that combined process is effectively, we can treat that as a conductance. Yeah. So let's not think about resistances anymore. We talked about conductance. So how easy it is for charge to move in a particular direction depending on the the voltage. And then finally, we can think of, for a particular ion, we can think of a voltage sort of built up just due to that component, not all of the components. And this is our particular model. So this is the voltage of the cell in total. This is the voltage due to the individual ion. This is the, this should be connected to here. You've got the pump current, and you've got the cellular membrane, and of course you've got the conductance of, the leakage and channel opening. Note, this is a variable resistor because that ion channel could be open or closed, or some kind of weird halfway open, halfway closed. So this model leads us to what's called the Nernst equation. So this is Walter Nernst. He was born in Prussia, so you could say he was Polish or German in the modern day. And what he did was he took Fick's law, he took the Einstein relation, he brought them together and developed what is called the Nernst equation. So let's look at this in detail. So basically what he's saying, the Nernst potential, so this is the potential, this thing here, which, sometimes described as an E and sometimes as a V. But basically it's the potential for a particular ion, not the entire cell. This is the potential due to a particular ion, and it relates the Boltzmann's constant, the temperature, the fundamental charge. So these are just constants. You've got this Z, which relates to the number of charges on the ion. So for chlorine, potassium, for potassium and sodium, it's the same. It's +1. Chlorine is -1, and calcium is +2. 2 charges. And then you've got this interesting concept that it's the logarithm of the concentration on the outside compared to the concentration on the inside. But that's weird, because we're thinking of the Nernst potential as in the voltage of the inside of the cell compared to the outside of the cell, and yet this is the logarithm of the outside concentration compared to the inside. If this is confusing, it's worth noting that the logarithm of the logarithm of n1 over n2 is the same as minus log of n2 over n1. So in other words, it's just because the standard way of presenting this is not to present it with that little minus. So it's just a question of direction. It's worth noting that chemists like to give it in this RT format instead of KT. It's the same thing, really. RT over F instead of KT over Q. I'm not a chemist. I'm a sort of physicist / electronic engineer, so I prefer it in that KT form. But, it doesn't really matter. Now, the Nernst potential, you can do some calculations for particular cells, and and you'll get something like this. So you'll get you can do a calculation for different concentrations, and the primary ions are potassium, sodium, chlorine, and calcium. Calcium, not so much. And for a neuron, these are the standard extracellular potentials, and you'll notice for a neuron there's much more potassium on the inside and much less sodium on the inside. And this is a bit weird. It seems like the cell's doing two things to fight itself, but I'll explain this with the action potential in the next lecture. There is a rationale, but wait for it. So, before we go into the in towards summing up and towards the next lecture, let me introduce the Goldman equation. So the Nernst equation was for a single ion type, so potassium, chlorine, sodium. The Goldman equation does it for multiple ions to get the overall voltage across the membrane, rather than the voltage just for that particular, or the potential for that particular ion. And of course, we mentioned before that the primary ions are potassium, sodium, and chlorine. There is calcium, but it really has another function, and it's a fairly minority effect for most of the high-speed bioelectronics. So again, you have these kind of components. The circuit model are these individual conductances across the cell membrane, and leakages across the membrane, drift diffusion across the membrane, and the ion channel for a given ion. You've got the Nernst potentials for each that build up. You've got then the pump that's continuously pumping out sodium, pumping in potassium, and of course you've got the cell membrane. And what we want to create is this much more simplified structure, which is just an overall pump and a single combined effect across this membrane that tells you what the potential is. Now the key difference in this, it looks very much like the Nernst potential, KT over Q with a logarithm. The key difference here is that what you're doing is you're adding up intracellular and extracellular concentrations. Note that chlorine is flipped because of its negative charge, but also we have this P factor, which is a permeability factor, which just basically allows these things to be added up and get a relative contribution. In the next lecture, what I want to do is take these basic concepts and move them towards something called the action potential, which is very important for neurons. These two equations they're fairly simple, but to really bring it forward, or to really bring understanding, I will give you some homeworks so that you can get a feel for what these numbers actually mean. Okay, thank you very much, and see you at the next lecture.